And all right, so let's go ahead and get started on section 3.4, charts and graphs. The first type of chart that we're going to look at, it's technically a plot, but I think of it more of a chart, is called a stem and leaf plot. And this is probably new for many of you. I can tell you it won't be a major point of emphasis in our course, but I want you to be aware of it. And some of you might think it's a really nice way to organize data. What we do with a stem and leaf plot is we look at the data set that we have, and in order to organize it from least to greatest, instead of just writing each individual number down, it's a little bit of a shortcut. Whereas I look at these numbers and I see that I have tens digits and ones digits. So what I'm going to do here is I'm going to create a stem using the tens digits in my numbers. And here I have 30s, 40s, 50s, and that's it. So I'm going to put 3, 4, and 5 over here in my stem. And those are the tens digits of the numbers that I have in my data set. And then I'm going to write down the ones digits over here where the leaves go. So I'm going to write down my ones digits. The first number I have is 30, so I put a 0 right here. And that number is not 0. That number represents the 30 from my data set because there's a 3 in the tens and a 0 in the ones. And that's how that represents the 30. The next thing I would do to write down 42 is I would put a 2 right here because that's a 4 in the tens digit, a 2 in the ones digit. That is the number 42 from my data set. And then I'm going to keep going with this. The next one is 37, 35, 44, 58, 41, 55, and 30. And so there's all my data points written in this stem and leaf plot. One of the things I can see at a quick glance here is that there are more 30s than anything else. That's easy to see at a quick glance. But the trouble is that this stem and leaf plot is what we would call unrefined because the numbers aren't arranged from least to greatest. So the next thing we're going to do is we are going to make a refined stem and leaf plot. And the way we're going to do that is by writing these from least to greatest. So I'm going to have 30, 40, 50 still for my stem. And as I look at the 30s, I have 0, 0, 5, 7. 0, 0, 5, 7. And that's just from least to greatest. In the 40s, I have a 1, a 2, and a 4. And in the 50s, I have a 5 and an 8. And now what I've made is my refined stem and leaf plot that has my numbers from least to greatest. You may love the stem and leaf plot. You may think, that's not so bad, but I'd just rather write all the numbers down. And that's okay either way. I do want you to know what a stem and leaf plot is. If you see something like this, that you're able to read it and understand what it says. If I wanted to find the median of this data set, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. So I can count from least to greatest. Let's see, there's 9 data points. That means it's an odd number, so there will be one in the middle. 4 will be lower, 4 will be higher. So I go 1, 2, 3, 4, counting from top to bottom. 1, 2, 3, 4, and I could see that the median would be 41. So it works the same as any other way of writing down a set of data, but it's a little bit of a shorthand because we don't have to write down the tens digit of each number. We just write down the ones digits over there in the leaves. I'm not going to set up a poll for this, but I want to give you a chance to practice. So take a minute and make a refined stem and leaf plot for this data set. And here in a minute or two, we'll do it together. But I want you to try it. If you can create one, then I know you can read one. And that's really what we're after here. All right, I'm going to go ahead and start creating the stem and leaf plot. If you have any questions or you see anything that you're not sure of or doesn't make sense, you let me know. Let's see, I have 60s, 80s, 70s, and that's it. Now, not every stem and leaf plot will just have three numbers over there in the tens column, but we're keeping things small and easy to manage. And I have 67, 85, 73, 63, 74, 84, 61, and 72. And so I can see that the 60s and 70s have the most, the 80s have the least at a quick glance. And then to refine this, I'll rewrite it with my 60, 70, 80, and I'll go least to greatest. In the 60s, I have 1, 3, 7. In the 70s, I have 2, 3, 4. In the 80s, I have 4, 5. At a quick glance, I can see that there's no mode. And if I wanted to find the median or the quartiles, I could do that from this stem and leaf plot. Are there any questions about how we made or how to read a stem and leaf plot? A question might be, what number does this represent? And it would be 73, not just 3. That would be a way that you're reading a stem and leaf plot. Okay, very good. Bar graphs. Bar graphs are probably something that you're fairly familiar with. We see them often, whether it's on TV or on a website when we're reading a news article or a sports article or whatever it might be. And what bar graphs are used for is they're used to show data that's in specific categories. A key thing about bar graphs is that they show the raw data. When we're given a bar graph and we've got numbers along here and we have our bars that we're looking at, we have specific categories, and those categories go down here along the x-axis. That's where our categories go, along the horizontal axis, the x-axis. And then we have a frequency that goes here on the y-axis. And it is possible to make horizontal bar graphs, but we're going to be primarily focused on vertical bar graphs, where our frequency is going to be on the y-axis and our categories are going to be on the x-axis. One of the things that's true about bar graphs is the taller the bar, the higher the frequency. So whichever has the tallest bar, that's the one with the most data points in that category. Another thing about bar graphs that I want to mention is that the categories here along the x-axis, they would make sense in any order. I could shuffle those around and it doesn't really change what the bar graph shows me, because what I'm interested in is the frequency of each category. And I can see that by looking here, and it doesn't really matter what order the categories are in. We'll see an example of that here in just a second. I do want to re-emphasize a key thing about bar graphs is they actually do show us the raw data. Not every graph we look at today is going to do that, and so that's a key identifying feature of bar graphs. Here's an example of a bar graph. A class of students has the following eye colors. 16 students have brown eyes, 6 students have blue eyes, and 2 students have green eyes. And, just to sort of begin our little refresher there, we have our categories here on the x-axis, and we have our frequency here on the y-axis. We can see the raw data. We can see 16 students had brown eyes, 6 students had blue eyes, and 2 students had green eyes. So, all those features of a bar graph are definitely present in that we can see the raw data. The tallest bar has the highest number of data points in there. And then the other thing that we talked about with bar graphs is these categories could be arranged in any order. So if I looked at this bar graph, I'm like, that's fine, but seems like it would make sense to me if you went from highest first, then the one in the middle, and then the lowest over here on the right. Well, if we just picked up that green bar and moved it over here, that would be just fine. We can put these categories in any order we want because the order doesn't really make a difference. If I want to rearrange them so that it's this way, it's perfectly fine to recreate my bar graph so that that's the way that it looks. Are there any questions about bar graphs? And like I said, it's something you're probably pretty comfortable and familiar with already. All right. A histogram. A histogram is sort of a special kind of bar graph. You can see we have frequencies over here on the left, and we definitely have bars, and we can see all the raw data. Let's say here we have hours of life for batteries. So batteries were tested to see how long they would last, and however many hours they would last is what we see in our bar graph here. And so like for 39 hours, we had 5 batteries that lasted 39 hours. We had 5 batteries that lasted 40 hours. And that's what we can see here in this particular graph. What makes this a histogram is that histograms follow some specific rules. They're like bar graphs, but they have specific rules that go with them. The categories that we have on the x-axis represent continuous data. So it's something that, 37 hours, 38, 39, 40, 41, 42. And what this means is we can't rearrange them. It wouldn't really make sense for us to pick this 42 hours up and, move it in there in between 38 and 39. That would really disrupt what this histogram is showing us. So we have continuous data, and it's presented without any gaps at all. You'll notice these bars go right up next to each other with no gaps, unlike the bars that we saw on our eye color. Those had gaps between them. The gaps could be bigger. You could take the gaps away, but it kind of makes sense to have them separated. Here, we're going to present this data without any gaps at all. Part of that is because the data is continuous. It goes 37, 38, 39, 40, 41, 42. I will say this. A good question might be, well, what if this went 43 and 44 and they weren't any 43s? So we have 43 over here and we have 44 after it. And when I look at the picture, what I see is there's this little bar for 44 right here, and then there's nothing right here. If you were to see a histogram like that, it doesn't mean there's a gap. What it means is there's a bar right here that just doesn't have any height, but there's still no gap. We couldn't say leave 43 out and just move 44 over. That would be not allowed. We've got to have our continuous data with no gaps. And if there happens to be a bar with no height, well, that's okay. We just can't leave the 43 out. I will tell you that in section 3.4, the bar graphs are more important. This is a special type of bar graph, and we're going to revisit the importance of this in sections 3.5 and 3.6. We're going to see histograms again on Thursday. For right now, I just want you to know that they are a bar graph. They're just a bar graph that comes with some special conditions. Okay, put bar graphs behind us and go on to line graphs. Line graphs have a very specific purpose. Line graphs are great for change over time. When we see something happening over a period of days or weeks or hours or years, a line graph is an excellent choice. Here we have an example of funds that were spent for road construction in some fictional town. And the years we have are 2010, 11, 12, and 13. This right away shows us that this is change over time, and our time goes on our x-axis. We want to make sure it goes chronologically, 10, 11, 12, 13. We wouldn't want to mix those up in some random order. We want to go chronologically, left to right. And then we can see here we have how much money was actually spent. The reason that a line graph is so good for change over time is because we can see when did it go up, when did it go down. It's really easy just at a quick glance to look at this and see, you know what? It went up from 2010 to 2011. While this is definitely related to the algebra concept of the slope, we're not going to calculate the slope. We're not going to have to do that. But I do want you to see that this went up. So we would call that an increase. The expenditures went up. It increased. And then when we look from 2011 to 2012, it definitely increased. And here, it increased more than it did from 10 to 11. And it increased because it went up. And because it went up at a steeper incline, that's how we know that it increased more than it did from 2010 to 2011. And then finally, over here on the right, when it goes down, as we read a graph left to right, the same way we would read a book. And here it's going down. And so there we have a decrease. So what we've got here, what we can see in our line graph, and the beauty of this being change over time is it went up, so there's an increase. It went up really sharply. It was a steep incline, so it increased even more in that year. And then because it went down, we had a decrease. And that's the main thing I want you to take away from reading a line graph. Also, I want to make sure that you're aware of line graphs are best for change over time. And the reason for this is because it's really easiest for us to spot our increases and our decreases. Any questions on that about line graphs? All right. A little bit of a review of proportions before we go on to our next graph that we're going to look at today. And we did plenty of proportions, especially in chapter 1 when we did geometry with similar triangles. Here, if we wanted to look at a proportion that was 4 over 25 is equal to x over 360. And I know that you're probably comfortable with this because of the work we did back in chapter 1, but that's been a while, so a little reminder is not going to hurt. When we have a proportion like this, the way that we solve for x is we cross multiply. Multiply this way, x times 25 gives us 25 times x. Multiply this way, 4 times 360. I don't know what that is. 4 times 360 is 1,440. And just to kind of pull you guys in for a minute, what do I have to do to solve this, to get x by itself? What do I have to do? Just a little reminder of the algebra that we did a while back. And just as a little reminder, we've got this x here we're trying to get by itself. I've got 25 multiplied by x, so I want to make 25 times x go away. All right, I'll take it, Kevin and Ashley. That's perfect. I want to divide by 25 on the left because that'll get these to cancel, leaving me just the x. If we divide by 25 on the left, we also have to divide by 25 on the right. And when we do that, we get 57.6. And so we've solved that for x. We found out that x is 57.6. The reason we do that review of proportions is because we're going to use proportions in the next type of graph we're going to look at. Pie charts or circle graphs. This is something, again, that we see these often in on TV, in articles that we might read. We see circle graphs, pie charts. I tend to call them pie charts, but I think circle graphs is a little more official. What pie charts are used for is to compare data that are in different categories. But unlike bar graphs, where we have different categories and we can see the raw data, what pie charts do is they show us relative proportions or percentages. So that's what pie charts are really good for. And we'll see an example of that in the next example we look at where we make a pie chart. We're going to take that eye color data that we had before. 16 students had brown eyes, 6 students had blue eyes, and 2 students had green eyes. And what we're going to do is we're going to make a pie chart out of this. And you're probably familiar with the idea that a pie chart is going to be based on a circle. Anybody remember, if I were to go all the way around a circle, how many degrees that would be? If we go all the way around a circle, how many degrees is it? Excellent, Ashley. Very good. 360 degrees. So what we've got here going all the way around the circle is we have 360 degrees that we need to allocate. We need to give some of those degrees to brown. We need to give some of those degrees to blue. And we need to give some of those degrees to green. Now, we don't want to go over here and just say, well, you have 3 categories, so we'll cut it into thirds. There you go, pie chart. That would work if every category had the same number of students in it, but it doesn't. We want to make sure we allocate these degrees in a proportional manner. That's why we're going to use proportions. So in this data set, I have 16 students with brown eyes. I have 6 students with blue eyes, and I have 2 students with green eyes. In the same way that the total number of degrees is really important to us here, the total number of data points is going to be really important to us here. And that total will be what we get when we add those up. 16 plus 6 would be 22, and 2 more is 24. And so what I'm going to do is I'm going to set up a proportion here. And that proportion that I'm going to set up is going to be based on the idea that 16 out of 24 students have brown eyes. 16 out of 24 students have brown eyes. So how many out of the 360 degrees do I want to give to brown when I make my pie chart? So that's the philosophy we're working under here, is how many out of the total equals how many out of the total. 16 out of 24 students is how many out of 360 degrees. Using that same approach that we did just a minute ago, we'll solve this proportion. We'll multiply and have 24x is whatever 16 times 360 is. Pretty big number, but that's all right. We're allowed to use calculators. 5,760. And then to get x by itself, we're going to divide both sides by 24. So I'll divide by 24 on the left. Those will cancel. Divide by 24 on the right. And I'll find out that x, the number of degrees that I'm going to give to brown, is 240. So when I draw my pie chart over here, I'm going to need to give 240 degrees to brown. If you're thinking, how in the world am I supposed to know where 240 degrees goes? You're not going to need a protractor. We're going to do our best to be fairly accurate, but we're just making a sketch. If all the way around is 360, then halfway around would be 180, and halfway to there would be 90. And then over here, this number, well, it's 90 plus 90 more plus 90 more. Okay, so that's going to be 270 over there. And so basically what I've done is I've sort of given myself some markers that will help me draw my pie chart. And the first thing I want to do is give 240 degrees to brown. So I start out by drawing a straight vertical line. And what I need to do is I need to go around the circle till I get to 240. And that's where I'm going to draw my line in for brown. I'm not going to get out a protractor. Doesn't have to be exact. I'm going to eyeball it right there and say, okay, that's 240 degrees. And this has now been given to brown. Let me know if you have any questions on anything we've done so far. 16 out of 24 students had brown eyes, so we set up a proportion. 16 out of 24 is how many out of 360? Solve that proportion to find out that 240 degrees need to go to brown, and that's what I've done in my picture over here. I've given 240 degrees to brown. Up next, we're going to do the exact same thing with blue. With blue, 6 out of 24 students have blue eyes. So I'm going to set up a proportion. That'll be 6 out of 24. Lost my connection there for a second. Hopefully y'all can still hear me. I just can't write. Okay, 6 out of 24 students. So how many out of 360 degrees? Again, we're setting up a proportion using that same philosophy. We'll cross multiply and have 24x is, let's see, 24 times, or 6 times 360 is 2160. We'll divide both sides by 24 and end up with x is 90. So I wind up with x is 90, which means I need to give 90 degrees to blue. Here's a little bit of a danger spot when drawing a pie chart. This is something that sometimes students have a little bit of difficulty with, but I think we can clear it up really easily. I'm supposed to give 90 degrees to blue. Well, if I draw a line here and want to give this 90 degrees to blue, I can't do that. Those degrees have already been given away. Those are already allocated to brown. I can't give those 90 degrees to blue because they're already given away. Instead, I've got to find 90 degrees over here in the unclaimed part that I can give to blue. There's two ways you could do that. Both are completely fine. I think what I'll do is I'll start at 240 here, and I'll start at 240, and from there I'm going to go 90 degrees forward. That would put me at 330. So I'm going to draw in a line that goes to 330. Again, we're just eyeballing this. I'm going to draw in a line that goes to 330. And then it's pretty close to 90 degrees. That's not too bad. And then so these 90 degrees have been given to blue. Then the only other color that needs to go on my pie chart is green. So I could just fill this in with green. But just to make sure, I'm going to do the calculation. Now it goes from 330 to 360. So it better be 30 degrees when I do the calculation. I'm going to go ahead and do it just to double check. That's 2 out of 24 students have green eyes. Is how many out of 360 degrees should go to green? We'll cross multiply, have 24x is 2 times 360. Divide both sides by 24. And sure enough, it's 30 degrees, which is exactly what I wanted it to be. And so we wind up with the creation of this pie chart right here that shows me relative proportions. As I look at this pie chart that I just created over here, when I look at this pie chart, I don't see the raw data anywhere. It doesn't show me raw data. What it shows me is relative proportions or percentages. I can see at a quick glance looking at this that more than half of the students have brown eyes. Bang, quick glass. And the smallest number of students have green eyes. Again, at a quick glance, I can see that. And that's sort of the value of a pie chart, is it lets me see things really quickly, just at a quick glance. I don't get the raw data, but I can make easy comparisons with a pie chart. One question that may be in your head right now is, okay, well, what's this question going to look like on a quiz or an exam or even in the homework? Because I'm not going to be able to draw a pie chart. And you're exactly right. You can't. There are a couple of different ways I could ask questions related to pie charts. One would be to give you a set of data like this and give you a series of pie charts and say which one is correct. And you could identify the correct one. Another way to go, and it's a question that I really like to ask, is just to ask, if you were going to make a pie chart for this data, how many degrees would you give to blue? And so you would figure out how many degrees would you give to blue, and 90 would be your answer. My assumption there is if you can tell me how many degrees you would give to blue, then you could tell me how many degrees you would give to brown or green. And I kind of get all of those questions answered with just one question. You'd use the same approach to get brown and green as blue. So if you can tell me the correct number for blue, then we're probably in pretty good shape. Are there any questions about what we did here with this pie chart before I have you try one? All right, outstanding. Favorite meal data was collected from some people. 6 people said breakfast was their favorite, 10 people said lunch was their favorite, and 14 people said dinner was their favorite. We're going to draw this pie chart together, but first, I want you to answer the question, what number of degrees should be given to dinner? So that's the poll that I'm going to set up, is strictly how many degrees would you give to dinner? So imagine that you're making the pie chart here and determine the number of degrees that should be given to dinner. We'll go another 30 seconds on this and then we'll look at it together. All right, let's see where we are on this one. Okay, unanimous. Outstanding. That's usually a really good indicator. All right. So just to answer this question, we don't have to go through the whole process of drawing the pie chart. You can, and we're going to, just so I give you another chance of seeing one get drawn. But just to answer this question, really, all we would need to do is say, well, what number of degrees should be given to dinner? First thing I'm going to need is the total, which let's see, that's 6 plus 10 plus 14, that's 30. And so I just set up a proportion here and say, well, let's see, dinner is 14 out of 30 people chose dinner as their favorite. And that's how many out of 360 degrees? Cross multiply, we'll have 30 times x is 14 times 360 is 5,040. And then just like we did before, we'll go ahead and divide both sides to get the x by itself. On the left-hand side, those 30s cancel, leaving just the x. And on the right-hand side, we have 50/40 divided by 30, which is 168 degrees. And we've answered the question, how many degrees should be given to dinner? Like I said, I want to go through the whole process of drawing the pie chart here, but as far as answering that question goes, that's all you would need to do. Once you figure out the degrees for dinner, then I'm under the impression that you could figure out how many degrees for breakfast and how many degrees for lunch. So we have breakfast, we have lunch, and we have dinner. And we had 6 chose breakfast, 10 chose lunch, and 14 chose dinner. I'm going to use this information to make a pie chart that has 360 degrees in it. We'll go ahead and start with breakfast over here. And so breakfast, let's see, 6 out of the 30 people chose breakfast. So how many out of the 360 degrees should be given to breakfast? And we cross multiply. And we have 30 times x is whatever 6 times 360 is, 2160. Divide both sides by 30, and we see that 72 degrees is going to be given to breakfast. Now, you might think, how in the world am I going to draw 72 degrees? Well, remember, we're just making a sketch here. So we've got 90, 180, 270, and 360. Start out with our vertical line, and we'll go to 72 degrees. And, well, we're ballparking this. So there's where I'm going to put my 72 degrees. And that much of my pie chart goes to breakfast. Okay, how many degrees for lunch? We'll go over and we'll kind of do the same work. We're going to say, well, 10 out of 30 people chose lunch. So how many out of 360 degrees should be given to lunch? We cross multiply, and we have 30x is 3,600. Divide both sides by 30, and we get 120 degrees should be given to lunch. Careful, I don't want to just draw a line here at 120 and say this is all lunch, because some of that has already been given away to breakfast. So what I need to do instead is I need to start at 72, and from there, I need to go 120 past it. Okay, well, so 72 plus 120 would put me at 192. So that's where the line needs to go. I'll go to 192. Again, we're just ballparking it. And so that's where my lunch section would go. And then kind of done at this point, the remainder of my pie chart has to go to dinner, just to make sure. We did the calculation for dinner. We found out that it was 168 degrees. Let's see, if I were to start at 192 and go 168 from there, where would that put me? Sure enough, at 360. So I feel great about it. And there's my pie chart with breakfast, lunch, and dinner sectioned off. I can see at a quick glance that almost half chose dinner as their best choice. When looking at the pie chart, I can't see the raw data, but I can see comparisons. I can see dinner was the most, and it was almost half. I can see breakfast was the least, just at a quick glance. Are there any questions about what we did with pie charts, using proportions to figure out the number of degrees? Okay. When the opportunity presents itself, we're going to talk about how to quote unquote lie with statistics in this chapter. We've seen a couple examples of that so far. And since we're talking about graphing today, we're going to talk about how to lie, quote unquote, with graphs. And here we see a graph of teacher salaries. And what we've got here is some town somewhere, 1990, 2000, 2010. These were their teacher salaries. And so by looking at this, we can kind of see we've got, that's about 30,000. And this is about 32,000. And over here, this is 38,000. So those are the numbers we're dealing with. And if you were to look at this and, let's say it's 2011 and you live in this town and you look at this graph and you're like, boy, if you look at that, yeah, it's an increase. And yeah, that's an increase, but it's been pretty flat for almost 20 years. Kind of looks like, teacher salaries haven't changed very much. And that's what we see in this graph. What I want to do now is look at this graph. And without even looking at anything, you can see this is teacher salaries again. And they went up a little bit, and holy cow, look how much the salaries went up there. This must be a totally different town. Well, let's see. We've got 1990, 2000, and 2010. It's the same years. And let's see, that's 30,000. That's 32,000, and that's 38,000. Wait, 30, 32, and 38. 30, 32, and 38. This is the exact same data on both graphs. When I look at this graph, it looks like, gosh, teacher salaries have gone up, but they've barely even changed. When I look at this graph, they went up a little, and then holy cow, they shot up like crazy. And it's the exact same data on both graphs. What's happened here is this. On the first graph, we can see that our y-axis starts at 0 and goes all the way up to 38,000. We have zoomed out. We can see the entire axis. We have zoomed out. We can see the entire y-axis. However, on this graph, we have zoomed in. What we've done is instead of going from 38,000 to 0, we have zoomed in on one particular part of the graph and just started our axis at 30,000. What we've done is we have truncated, which means chopped some off. We have truncated the y-axis. What that's done, when we truncate, it zooms us in on where the data is located. So instead of seeing the entire axis from 38,000 all the way down to 0, what we've done is we have zoomed in on just this piece right here from 30,000 to 38,000. Neither one of them is lying, technically. They're both showing the exact same data. It just kind of depends on who you are, which graph you might want to show. If it's 2011 and you're the teachers, you want this graph in the newspaper because you want to say, look at this. Our salaries have been flat for 20 years. We're in desperate need of a raise. If you're on the school board, you want this graph in the newspaper because you want to say, well, look at this. I mean, we gave them a salary raise here, and then we gave them a huge raise between 2000 and 2010. They don't need a raise. The salaries have gone up like crazy. It's the exact same data. It's just depending on which side you're on, you may want to influence people by presenting the data in a certain way. What I want you to make sure you're aware of is when we zoom out, this makes the change look less drastic. It makes the change look small. When we zoom out, the change looks small. It looks less drastic. It looks less dramatic. It doesn't look like there was that much of a change at all. When we zoom out, the change looks smaller. When we zoom in or truncate, same thing, the change looks more dramatic. It's like, holy cow, look at that change. It's tremendous because we zoomed in. So make sure you have that clear in your mind that if we zoom out, what we've done is we've pulled way back and the change looks less dramatic or less drastic. It looks small. When we zoom in or truncate, the change looks more dramatic. It looks bigger. Holy cow, look at that change. Because we zoomed in right on where the change was located. Another misleading trick you can do with graphing is in a bar graph, instead of changing anything on the axis is still the same. But if we said these are textbook prices in 2010 and 2020, and it's true that if you look at the heights of the bars, there is an increase. But what's been done here by the person making this graph is look how much wider the 2020 bar is compared to the 2010. And by making it that much wider, because it takes up so much more space on the page, it makes the change look like it is huge. Is there an increase? Yes, it went from here to here if they were the same width. But by making it really wide and making it take up so much of the page, it makes it look even more significant than it really is. There are some examples of this on pages 223 and 224 that you can take a look at. The key here is there are a couple of different ways that you can manipulate a graph to sort of illustrate a point that you're trying to make. And I would just want you to be aware of those. A couple of things to sort of wrap us up for today. It's a relatively short section, 3.4. There we talk about stem and leaf plots, we talk about bar graphs, histograms, line graphs, pie charts, and a little bit about how to lie with different graphs. But there's not, this is a relatively short lesson. But just to sort of summarize, one of the most important things here is what is each graph used for? What is it best at? What is its purpose? And remember when we talked about bar graphs, one of the key things that they do is they show the raw data. If you want to see the raw data, a bar graph is an excellent choice. Also, just be aware that we can arrange the categories in any order. If we want to move those categories around, we can. It doesn't matter. A histogram is a special kind of bar graph that shows continuous data with no gaps in between the bars. That's going to be really important for us in sections 3.5 and 3.6. But right now, it's a bar graph that has some special conditions attached to it. Line graphs. What the line graphs are best used for is to show change over time. And that's because we can see the areas where it has increased and where it has decreased. And then finally, pie charts. Pie charts show us relative percentages or relative proportions. We can't see the raw data, but we can see big conclusions at a quick glance, which is the most, which is the least, is something more than half, is something about 1/4, like those kinds of relative percentages and proportions are what we can see in a pie chart. So make sure that you know what each type of graph is best at, what